So, displacement operator, you know that this is exponential of alpha A dagger minus alpha star A, where A and A dagger are the annihilation and creation operator. Alpha is a complex number. And then we introduce this S parameterized displacement operator. This is actually not displacement. So, which is e to the power S mod alpha square by 2 into d of alpha. So, S is a complex number. Okay. Now, of course, this is not, this is a unitary operator, this is not a unitary operator, okay, in general, I mean unless I take S to be 0, right. And then we considered this operator, which is this complex Fourier transform of your displacement operator. Okay. So, this is basically the complex Fourier. So, for complex Fourier transform you have this factor, because I said that this is important in order to make Fourier transform and its inverse also having the same factor. Okay. So, this is beta belonging to C d square beta exponential of alpha beta star minus alpha star beta. So, this is the corresponding factor for Fourier transform, then d of beta is. Okay. So, this is basically the complex Fourier transform of this displacement operator. Okay. Right. And we have also seen that this you can write as your displacement operator, then T of alpha 0, no, not alpha 0, this is 0 s, yes, T of 0 s, and then d of alpha inverse, which is d alpha inverse, basically this is d of, okay, you can write d of. So, d of alpha inverse is equal to d of alpha dagger is equal to d of minus alpha. Okay. So, this is what we have seen. So, the alpha dependence of this T alpha s is through these displacement operators, right. And we have also seen that this operator is Hermitian if you take alpha s to be real. For real parameters, this is Hermitian, whatever be your alpha, it does not matter. Okay. So, this also we discussed, and then via using this example that f of lambda is equal to lambda to the power a dagger a, where lambda is a complex number. I mean this is of course bounded for mod lambda less than 1. So, via using this example we could manage to show that your T of 0 and s is equal to 2 by 1 minus s times s plus 1 by s minus 1 to the power a dagger a. So, this is an operator, this is a just a number. Okay. So, this is what we could manage to show, where basically your lambda should be, this lambda should be s plus 1 by s minus 1, something like that. Okay. So, from there you will get this form. Anyway, so by looking at it you see that if s is real, then of course this is a Hermitian operator. Okay. And we have also seen, therefore, from here it follows that T of alpha s, which is this displacement part. So, basically this will be 2 by 1 minus s d of alpha s plus 1 by s minus 1 a dagger a d of alpha inverse or d of minus alpha. Okay. Which one? Alpha beta star minus alpha star beta. Yes, yes, that is the Fourier coefficient. Okay. Right. So, now you look at here. So, if you look at here, you see that this is so how does it look like? In fact, I want to, so here I have seen the S dependence of T alpha S and also the alpha dependence. Now, this is a kind of spectral decomposition, because if S is real, then you see that what will be this? This is basically the eigenvalues. So, like T of alpha S acting on D alpha on, let us say, n. So, what is n? N is the eigenvector of A dagger A corresponding to eigenvalue n. So, if I do that, then what you will see is that this is your what will be this if I so I am applying this. Okay. So, what will be that? This is basically 2 by 1 minus s d of alpha, and then s plus 1 by s minus 1 A dagger A acting on n, right. And so, this is 2 by 1 minus s. So, this will be n. So, this is s plus 1 by s minus 1 to the power n d of alpha acting on n. So, you see that this is eigenvector of this operator corresponding to this eigenvalue, and these are all orthogonal to each other, because if you choose different values of n, these are all orthogonal to each other, because this is this is unitary operator. Okay.
So the T0 is a choice, or like you can derive it.
Which one?
T0 is.
No, T0s is, this is my Ts. So, you choose alpha is equal to 0.
Yes.
So, that is your T0s. Okay.
Yeah, but like that should be an input, like to find what T alpha S is.
Yeah, that is true. This is
So
your,
you're choosing your T0S to be that.
yeah, this we have proved that this T0s has to have this form. Okay. Right. This we have proved, right, in last
Yes.
class. Yes. So, this is what we have proved. That, I mean, by comparing with this operator, you can figure out this is the form. Okay. Okay. Right. So, now you see that the S dependence of this operator, alpha dependence is through this displacement operator, but S dependence, it comes through these eigenvalues. Okay. Eigenvalues of this operator. Okay.
Why do you say that it's like a spectral decomposition?
Kind of, because this is not Hermitian for generic S, only for real values of S this is Hermitian. Okay. So,
So for PLS, this is a spectral.
this is a spectrum. I mean, these are orthogonal. I mean, of course, if you choose n differently, but maybe you can say this is right eigenvector or something like that. Okay. Okay. And if I now try to figure out the behavior of this operator, so then if I look at the trace norm, so T of alpha S, which is by definition is equal to, so alpha S is D of alpha T of 0s D of alpha inverse. Now, this trace norm, that this is basically what is that? Trace of T of alpha S dagger T of alpha S, and then square root of that. Okay, this is your norm. So, this norm, that under unitary transformation, this norm does not change, right? And as a result, this is same as T of 0s. Okay, this is according to our notation, we call it as, no, it is just simple this of 2. And similarly, you can show that T of alpha is 1 known. So, which is basically square root of least upper bound over all psi which are normalized of this expectation value. T of alpha is dagger, T of alpha is psi. So, if you calculate this quantity, once again, this does not depend upon what d alpha you have chosen. So, this is same as T of 0 is 1. Okay. And the third is T of alpha is 2. What is that? That is trace of square root of T of alpha is dagger, T of alpha is, again that will not depend upon this displacement, the unitarity. So, this is basically same as T of 0 is 2. Okay. Right. So, if this is finite, then that means if this is bounded, this is also bounded. If this is finite, I mean if this is finite, then this is also finite, and so on and so forth. Okay. Right. So, what can I say about okay, now what about this T of, so what is this T of 0 s? If I look at it, this is 1 upon pi beta belonging to C d square beta, this is 0. So, basically this is d of beta s, right, and this is 1 upon pi beta belonging to C d square beta d of beta e to the power s mod beta square by 2. Okay. Right. Okay. So, what can I therefore say about this one? So, therefore, this T of 0 s, its norm, or let us say this is square. So, this square is equal to, what is the definition? Definition is, what is that? This is trace of T of alpha 0 s dagger T of 0 s, right, that is the definition. And now, if I use this, this will be trace of 1 upon pi, so 1 upon pi square actually, then this is beta star belonging to C d square beta prime, then this is d of beta dagger. So, this is minus d beta, and then from here you will have d of beta prime, then e to the power. So, here it is dagger. So, basically you will have a star beta square by 2 and plus s beta prime square by 2 trace of this, right. I think so, yes. Okay, because you use this expression, right. Okay. So, basically what you will have, you can take this trace inside, and this we know that trace of d of alpha d of beta is equal to what will be that? Okay. So, this is pi times, right. I mean basically this is d of, now you can have exponential of half alpha beta star minus alpha star beta and then d of alpha plus beta, right. And so, this is exponential of half alpha beta star minus alpha star beta into trace of this. Now, trace of this is pi times delta, I mean 2 dimensional delta function of alpha plus beta, right. I think this is what you will have. Okay. So, is that correct? Yes. So, that is what you will have, and this you know because your beta is minus alpha. So, therefore, this is minus mod alpha square plus mod alpha square. So, this will get cancelled. So, basically what you will have is pi of delta 2 alpha plus beta, right. Okay. This is what you will have. So, now what you can do is this is 1 upon pi square beta beta prime d square beta prime. Now, what about this trace? This will be here, you will, this pi will get cancelled and then you will have delta 2 of beta prime minus beta. So, you can choose beta prime to be beta. So, basically you will have only one integral over beta, this will go away and then e to the power. So, your beta prime is equal to beta. So, a star beta square by 2 plus s, this is again. So, therefore, this is s plus s times beta square by 2. Yes. So, this is basically, no, let me erase this part. So, this is so this is exponential of real part of s times beta square, okay, right. This is what you will have. Now, you see that, so when will it be finite? This will be finite only when real part of s is negative, right. Okay. So, therefore, this operator is a bounded operator. So, therefore, I can say T alpha s, because that is same as, I mean at least norm wise, this is bounded for real part of s being negative. Okay. Is that clear? Yes. Okay. In fact, you can also show that this is finite quantity if real part of s is negative. So, this is finite, this is also finite, and this is finite if real part of s is less than equal to 0. So, there is slight extension of the domain. Okay. So, you can actually calculate all these three from these expression, it is not difficult. Okay, maybe I will just tell you the result, then it will be easier to figure out. You just use that expression for T of 0 s and then it will follow from there. So, norm of this thing we already figured out. What you can show is that T of alpha s 2 is equal to 2 by 1 minus s magnitude minus 1 plus s, okay, and T of alpha s 1 non, this is equal to 2 by 1 minus s magnitude of that. Okay. So, So, this you can just figure out from that expression of T 0 S. Okay. So, you see that yes, this operator is not Hermitian for complex S, but it has some nice properties. You can figure out its eigenvalues, eigenvectors and all that, okay. Which was displacement operator, we know that is unitary, but yeah, finding out the eigenvectors of displacement operator may be tricky. Okay, okay, good. So, now let us go back to the distribution functions and then I will come back to this issues once again. Let us go back to the distribution function first. Okay. So, I will first talk about the okay. So, let me erase this part. Okay. So, in classical probability, you know that if I have a probability distribution, I can specify also these probability distribution through its moments, right, different moments. Right. So, if I have a random variable, okay, x, which can take values small x and there is some probability, let us say it is p of x, then I can figure out, you know, all these x to the power r, I mean maybe let us call it as p of x, okay, x to the power r p of x dx. Okay. So, that will give me, so for all different values of r, that will give me the moments, and once I know the moments, in principle I know the probability distribution, right. This is what we understand from classical probability theory, and there is something called moment generating function. So, that means you provide a function, by differentiating that function you can figure out the different moments. Okay. So, and these moment generating functions are, you know, basically these characteristic functions. So, classical probabilities are described by their characteristic functions, which will be the moment generating function. So, same thing I can do in the case of distribution functions, I mean the phase space distribution function. So, what I can now, so let me first start with the p distribution, which corresponds to the normally ordered case. So, the characteristic function corresponding to normal ordering. So, I call chi, this is normal ordering corresponding to a rho, and this is a function of, you know, complex number beta. And how do you define it? So, the definition is that you take trace of your rho and then this displacement beta, and now it is normal ordering. So, A's value should be equal to plus 1. Okay. So, this is how we define the characteristic function corresponding to the normal ordering. Okay. And rho is the density matrix. Rho is your density matrix, because from density matrix itself you want to go for the distribution functions. Okay. And this, if you look at trace of rho, and this is e to the power s. So, s is plus 1. So, mod beta square by 2 d of beta. So, this is what you will have, and then I use the normal ordering form. So, normal ordering form tells me that this is rho e to the power mod beta square by 2. Normally ordered form of this is e to the power minus beta square by 2 e to the what is that beta a dagger e to the minus beta star a. Is that clear? You know, if you split it, this is what our displacement operator is. So, if you split it using this Baker Campbell formula, then you will get this part. Okay. This is what we discussed, at the beginning, that if you have these two operators a and b such that this is equal to 0 is equal to a b b, then you can write e to the power a plus b as e to the power minus half commutator e to the power a e to the power b, right. This is the Baker Campbell formula. So, now you will have to use appropriately. So, your a plus b is, a you choose as beta a dagger and b you choose as beta minus beta star a, because your d of beta is exponential of beta a dagger minus beta star a. So, that is your this part. Okay. So, and this condition is satisfied here. Okay, good. So, basically these two terms will cancel and what you will have is trace of rho e to the power beta a dagger e to the power minus beta star a. So, this is your characteristic function for normal ordering. Okay. Right. Now, how does it help? So, the question is that this characteristic function, I do not know a priori whether this is square integrable, in the sense that whether the complex Fourier transform of this characteristic function exists or not, that I do not know beforehand. Okay. For some density matrices, of course, the complex Fourier transform of this will exist, in the sense that this will be square integrable. For some other density matrices, that Fourier transform may not exist, because that is not square integrable. Okay. And if it is not, if it does not exist, then we will have to take further action to use it, but for the time being let us assume that such characteristic function exists, in the sense that its Fourier transform exists. Okay. That means it is square integrable. Okay. If it is not square integrable, we will have to do bit, you will have to go to bit technical details, but that will do. But for the timing, let us assume that this exists. Okay. Right. So, now you have this characteristic function. Now, how to go about distribution function, like in the case of classical probability theory. So, how do you get distribution function? Basically, you look at the Fourier transform of this characteristic function, that will give you the distribution function. Okay. So, what you will do is you will call the this complex Fourier transform. So, so this time you should be careful. So, here I will take pi square. Okay. Because so beta belonging to C, this square beta. This is the complex Fourier transform, alpha beta star minus alpha star beta chi n rho beta. So, this is the complex Fourier. Of course, generally Fourier transform I get 1 upon pi, okay, complex Fourier transform, but this is the fact 1 upon pi, extra 1 upon pi factor is there.
Is this full transform because is it equivalent to taking this trace with t instead of this d? Earlier that t you had introduced.
Yeah, that will come. I mean, here so far it is in terms of this d. Yes. So, basically that is the idea. Yes. Okay. So, this is okay. So, this is kind of complex Fourier transform of this characteristic function, right. Okay. and conversely also you can write in rho beta, which is, so in this case there will be no factor d square alpha e to the power minus alpha beta star minus alpha star beta, then p rho alpha alpha star. So, this is the inverse Fourier transform of this p function, and look at here, there is no factor. So, this is what is known as we discussed also earlier, and we will see again that this is the Glauber Sudarshan p distribution function. Okay. When the Fourier transform of this does not exist, we will have to do little bit of go to some technical details and do that, but that is okay. Yes. So, now if you look at the definition of this function, so this is your trace of rho d of beta then s is equal to class 1, right. Now, if I take this Fourier integral inside of this trace, that I can do. So, then effectively this is what was the definition of your, yeah. So, effectively you see that, I mean, this expression is 1 upon pi trace of rho and then t of alpha s is equal to class 1. Is that a correct statement? Look at this definition of T alpha s. So, if I introduce this chi here like this and then take this integral inside the trace, this is what you will have. So, what does it mean? It means that, look, s is plus 1. So, this is a Hermitian operator, and we know that what are its eigenvalues, etcetera, eigenvectors. So, basically you perform measurement of this Hermitian operator on the state, and whatever average value you get, of course, this 1 upon pi factor is there, that will give you the p distribution. Okay. And we will see that similar thing happens for Wigner distribution, for Q distribution, everything. So, this is a kind of measurement based interpretation of this p distribution, provided, as I said, that these Fourier transform of this exists. Okay. If it does not exist, still we can give, but it will be kind of approximate.
So, basically T alpha is comma 1 is one Hermitian operator.
Hermitian operator, yes.
So, it's like one measurement.
Yes, you measure this Hermitian operator when you prepare your system in the state rho and get the average value. I mean, 1 upon pi times that average value will be your p distribution function.
There are two elements, right? It has to be square integrable and then the Fourier transform is square.
Square, if it is square integrable, of course, its Fourier transform exists. Huh? Yeah.
And
I
then
mean,
the other assumption was that you can take a trace of say
yeah, I mean that because it is square integrable, this entire integral will be convergent and all those things you can do. So, that is not any extra assumption. But one should be careful about p distribution, as I said, because most of the times it is singular. So one should be careful about that. Okay.
And singularity arises because the Fourier transform is not existing.
Exactly, exactly. Okay. So, now, so that was about p distribution. Again, we will have to come back to it time and again, but for the timing this is fine. Okay. So, I think we described it in terms of maybe some factor is there trace of rho and then the delta function like a dagger minus alpha star delta of a minus alpha, something like that we defined initially. Okay. So, basically this is proportional to this operator in terms of delta function. Okay, good. So, now let us talk about Wigner distribution. This we talked about earlier also, but now in a systematic manner. So, this is again corresponding to symmetric ordering. Okay. So, we have seen that if f is a bounded operator, then we can have a representation of f in terms of displacement operator. So, 1 upon pi alpha belonging to C d square alpha trace of f d alpha d of minus alpha, and we know. So, this is your weight function, and we know that if f is bounded, then this weight function is also square integrable and vice versa. In fact, you can show that this f is equal to norm of this weight function. So, let me call this as f of alpha. So, norm of this f, and this norm is defined as 1 upon pi, I mean square root of that integral alpha belonging to C d square alpha mod of f alpha square. Yes. So, that is your norm. Okay. Anyway, so this we have seen, right. So, now let us look at this weight function. Let me call these as yeah. So, let me call these as rho symmetric ordering of alpha, which is trace of rho d of alpha. Okay. Right. And this according to so this is basically trace of rho d of alpha s is equal to 0, right. So, this is my characteristic function. In fact, why this is characteristic function, because you see if you take the trace of any operator f and rho. Okay. So, basically what you will have is from here. So, this is 1 upon pi alpha belonging to C d square alpha trace of f d alpha multiplied by trace of rho d minus alpha, right. And you see this, is that correct? Yeah, this is correct. So, you see that this is your characteristic function symmetric ordering minus alpha, right. So, you see that when I take the average value of operator with respect to my state, these are the two things which will come. These weight function corresponding to this operator, which we call f of alpha, and this characteristic function. And this is the generic case irrespective of whether you choose S ordering, I mean symmetric ordering, normal ordering, anti-normal ordering, it does not matter. Okay. But we will have to be careful. I mean, this is not generic in terms of displacement operator, it is generic in terms of this t alpha s, and that is what we will tell you. Okay. For symmetric ordering, this is fine, because anyway s is 0, it does not matter much, but for other k ordering this will matter. Okay. Yeah.
Explain this formula. How did you break up the trace into the product of trace?
So, f is this one, right.
Yes.
So, now you take multiply by rho and take trace.
Oh, okay. The other one is a number. Right?
Yes. Okay. Now, this characteristic function is it is this in this case. So, it has certain properties that this is square integrable. In the case of p distribution, we did not know whether this is square integrable or not, right, but in this case it is known that it is square integrable. So, this is alpha belonging to C d square alpha if I take S rho alpha mod square. So, this is basically this is my norm. Okay. So, this you can show because okay. So, this is for you to prove, given that this is the form, you can prove that this is nothing but trace of rho square given this form. Okay. How will you do that? Simple. Take f is rho itself. Okay. If you take f is rho, then this is your characteristic function and this will be the complex conjugate of the characteristic function, because rho is Hermitian operator. So, therefore, this is what you will have, right. And because rho is a density matrix, we know that this is less than equal to 1 and equal to 1 when rho is a pure state. Okay. And from here, because S is equal to 0, so this is a displacement operator. Displacement operator, what will be the maximum value what can this be maximum? So, this is less than equal to 1, right. Okay. And alpha is equal to 0, of course, this is what? This is trace of rho which is equal to 1. Okay. So, this is a well behaved function, this characteristic function. Now, what we do is, just like in the classical distribution case, we go to the Fourier transform of this characteristic function and that will give me the Wigner distribution. So, the Wigner distribution, this is Wigner distribution of rho. So, this is again, as I said, in the symmetric ordering case you will have to take this factor 1 upon pi, because whether you so from both side anti-normal and normal ordering, this is what this. So, basically this is actually the complex Fourier transform exponential of alpha beta star minus alpha star beta times. Okay. So, this is the complex Fourier transform of characteristic function. So, that is your Wigner distribution. Okay. And if you invert it, so invert, you will get the characteristic function. The same factor will come minus alpha beta star minus alpha star beta, then W rho alpha alpha star. Okay. So, this is the inverse characteristic function. Okay. Is this fine? Okay. So, now let us look at this rho. So, rho was your, so f of f is this, and this is for any bounded operator. So, rho being a density matrix, it is also bounded operator. So, I can use this expression where rho is equal to 1 upon pi alpha belonging to C, maybe I will call it beta, d square beta. So, the weight function in this case is the characteristic function, right. So, this is symmetrically ordered characteristic function, then d of minus beta. Is that clear? This is the expression for the density matrix, okay. That is also a bounded operator. Okay, good. Now, you introduce these expression for, I mean, in terms of this Wigner function. So, use this expression here, right, which is the which is this Fourier transform of the Wigner function or inverse Fourier transform, whatever you want to call. So, what you will get is this one is equal to 1 upon pi alpha belonging to C d square alpha omega rho alpha alpha star, then 1 upon pi beta belonging to C d square beta e to the alpha beta star minus alpha star beta d of beta. I mean, I had to change this minus beta to beta, but anyway for this case it does not matter, right. So, now what is this? This is, if you recall the definition of T alpha s, then this is your T of alpha 0. Okay. So, this is 1 upon pi alpha belonging to C d square alpha rho alpha T of alpha 0. Okay. And this is legitimate because, you know, if I look at the Wigner function, the way I defined it, you know, it will, I mean, Wigner function is real function, okay. So, that one can figure out. So, these are real coefficients and these are Hermitian operators. So, therefore, this itself is a Hermitian operator, and rho is a density matrix, obviously it is a Hermitian operator. Okay. Right. So, now you see that this is your rho in terms of Wigner function and this T operator. Okay. Right. Okay. So, now I think we discussed, I mentioned it today itself, that your T of alpha s, it has this representation 2 by 1 minus s d of alpha s plus 1 by s minus 1 a dagger a d of minus alpha, right. This is what we mentioned in the beginning. So, now if I take, therefore, T of alpha 0, this is 2 d alpha minus 1, because s is 0 means this is minus 1 to the power a dagger a d of minus alpha. Now, what is this operator? This is parity operator, right. It has eigenvalues plus minus 1, right. Okay. Okay. So, therefore, if I look at now the Wigner distribution, which we defined as the Fourier transform of characteristic function, okay. So, now this characteristic function is therefore, now what is this characteristic function? So, you know that this characteristic function is basically trace of rho times displacement operator, right. This is how we define the characteristic function. So, therefore, what you will have is this is trace of, so I can take out this. So, this is, you can write it as trace of rho times the displacement operator. So, this therefore, what I can do is I can take rho into 1 upon pi beta belonging to C d square beta e to the power alpha beta star minus alpha star beta, then d of beta, okay. Because this is your trace of rho d of beta, isn't it? Was it not the case, this characteristic function? Yeah, so you just use that here, okay. So, now you can figure out that this is nothing but your t of alpha 0, right, and which we have already mentioned that therefore, your Wigner function basically it is trace of rho t of alpha 0. You remember we got similar expression for p distribution also, right. I mean there is a factor also there, but otherwise, yeah, I think for p so this is your Wigner distribution alpha alpha star. For p distribution we had alpha alpha star is equal to 1 upon pi trace of rho t of alpha and 1, I mean s is equal to plus 1, right. This is what we have seen. So, again you can interpret it like this is Hermitian operator. So, you measure the Hermitian operator on the state, the average value will be your Wigner distribution. Okay. So, as I said W rho alpha alpha star, this is equal to W rho alpha alpha star. Why? Because T of alpha 0 is a Hermitian operator. So, therefore, this is real. Okay. This is normalizable also in the sense that d square alpha W rho alpha alpha star mod square. I mean this is basically real, so it is fine. So, this should be because symmetric ordered characteristic function is Fourier transform of this. So, therefore, this should be equal to 1 upon pi alpha belonging to C d square alpha symmetric order characteristic function of this. Do you agree with me? Because this is the Fourier transform of this one, right, and this is square integrable. I mean this is also square integrable. So, therefore, this is what you will have, okay. And this we know that this is trace of rho square and which is less than equal to 1. So, you see that this is basically kind of normalizable, okay. So, okay. So, this is a square integrable function, you can say. So, this means that alpha alpha star is square integrable, which is anyway it is true, but yeah, because you have already used this characteristic function. Okay. So, Wigner function is real. In fact, all the distribution functions are real that you can prove, because it will come as the some real factor times trace of such Hermitian operator. So, it has to be real. So, this tells you that Wigner function at any alpha is finite, okay, because it cannot go infinity, right. In fact, one can prove that also. Well, this does not tell you that it cannot go infinity, because at particular point it may happen that this has singularity, still this integral is finite, that is possible, but we will show explicitly that this is indeed a finite quantity, bounded quantity between -2 and +2. Okay. So, yeah, so this is what we will show, but before that let me see whether I can skip this thing. This is too many things I will have to do. So,
At some point you wrote that the integral of the symmetric characteristic function is also less than equal to 1, implies that the characteristic function is less than equal to 1. That also did not happen.
yes, yes, but I mean the symmetric ordered characteristic function is actually it is square integrable.
Yeah, but so just the integral be finite
Need not be, yes, yes, of course, but one can what was the expression for the symmetric order? This is
the one that you used.
this is the thing, right? Okay. Now, displacement operator, if I take trace of that, so of course this is unitary operator, right. So, the question is, what is the maximum value this can have? Yes. So, therefore, I mean magnitude of this. So, therefore, this is always bounded. Okay.
Yeah, because it's unitary, we can split it into two parts. So we can find another unitary which is u square d beta by 2 times d beta by 2.
Yes, yes.
And under trace, okay, no, sorry.
Yeah, what you are saying is that, can I write it like this? Trace of d of beta by 2, d of beta by 2. Can I do that?
We can do that, but I was trying to move things within trace, and then but then that will not do anything.
That will not help.
Not
Yeah, because you need dagger here. Okay. Yeah, so I'll have to go little bit away from this for the time being, and then I'll again come back to this, because I need to prove that -2 less than equal to okay. Now, this perhaps you can prove also directly. What is your W rho in terms of trace of rho and then T of what is that? Alpha 0, right? Isn't it? Okay. And now this is trace of rho. Now, T of alpha 0 in terms of the displacement operator, what was that? I have written somewhere like here, yeah. So, alpha 0 is this one, right? So, this is 2 times what is that? D of alpha minus 1 to the power a dagger a d of minus alpha, right? Is that clear? Okay. So, this is 2 sum over n is equal to 0 to infinity trace of rho d of alpha minus 1 to the power a and minus 1 to the power n n n d of minus alpha. Is that a correct statement? So, you write this as sum over n this thing. Okay. This is spectral decomposition. So, therefore, this will be 2 times n is equal to 0 to infinity minus 1 to the power n. What will be this? So, trace of rho, this is d alpha acting on n and then d alpha acting on n dagger, or yes, is that correct? This is what you will have, and for this you will have this thing, okay, right? D alpha acting on n and then d alpha acting on n dagger. So, this is what you will have. Okay. So, basically this is 2 n is equal to 0 to infinity minus 1 to the power n n d of minus alpha rho d of alpha n. Is that clear? So, you are taking expectation value of rho with respect to the state, displaced number state, right. Okay. So, what will be the maximum value that W rho alpha alpha star can take? I mean, magnitude of this, or even if I do not put this thing because this is real. So, the maximum value this can have is class 2, right, because you see these are orthogonal for different n. Okay. So, is that a correct statement that this is less than equal to 2, greater than equal to minus 2? Can I say that from here? Yes or no? Yes.
If I assume that minus 1 is not there,
Yeah.
then taking summation over this
Is trace of rho.
will
Trace of
be
rho.
1.
Yes. So, this is 2. Yes, but now you have minus signs are also there.
So maximum value will be 2 even if there is
Hmm.
minus 1. So
What about the minimum value?
So it's like alternating series of numbers, which if you remove the signs differences, it adds to 2.
Yes, to 2.
So if you take alternating one version of that, it cannot be greater than 2, of course.
Right.
It cannot be less than minus 2 also, because largest number is 2. So if that happens to come with minus sign, least number will be minus 2. So
Okay.
yeah, I mean the same thing I can do with all the factors with minus 1 and then
Yes, right, exactly. So, therefore, this is correct, right. Now, when this maximum value is achieved for what sort of rho?
pure state, and then also n should be the corresponding n should be
For all displaced number states, okay, this should be either 2 or minus 2. Is this a correct statement? I mean, for given value of alpha, of course, for given alpha, all these displaced number states are plus 2 eigenvalue or minus 2 eigenvalues, right. I mean, if I take rho itself is this, okay. So, okay. So, you see that this Wigner function, therefore, it is bounded, I mean, everywhere this is bounded, not just this integral is bounded, everywhere this is bounded, integral is also bounded, this is real, square integrable, all those things are there. Now, the major question is, can it be negative? Yes, it can be, right, because if I choose n to be even, and so d alpha of that even Fock state, if I choose rho as that, then it will be minus, no, not even, sorry, odd, yeah, n to be odd, then this will take minus 2 value. So, therefore, Wigner function can be also negative. So, unlike classical probability distribution, phase space probability distribution, Wigner function can be negative. Okay. So, you see that this is a peculiar thing. If you look at the phase space, at some region of phase space Wigner function can be negative, at some other region it has to be positive, so that this normalization is satisfied, otherwise it will not be there. Okay. In fact, this is also true that if I take alpha belonging to C d square alpha w rho alpha alpha star, this has to be equal to 1. So, this is like a probability distribution. So, therefore, if some points it is negative, some other points it has to be positive, and as a result this is not a proper probability distribution, and this is why we call it as a quasi probability distribution. All the phase space distribution functions of quantum mechanical states, except for one, except for Q distribution, these are all quasi probability distribution functions. In fact, more than that, you can express, as we mentioned some time back, that you can also express it as a function of the quadrature operator, quadrature variables, where your alpha is equal to x plus I p by root 2, and alpha star obviously is equal to x minus I p by root 2. So, these are real variable. So, what one can prove is that if I integrate out d of p w rho x p, this can be negative, of course, this can be negative. So, to make our life easier, let me take it to be a pure state, okay, this rho to be pure state. So, if I integrate, so this is marginal. So, what you will see is that this is psi of x square. So, the position probability distribution of the state vector. So, we will prove this also. I mean, once you take the form of x p, and similarly if I take w psi x p, this will be the momentum. So, this is the Fourier transform. Okay. So, let me call it as psi tilde. So, psi tilde is the Fourier transform of this square. Okay. So, Wigner function is somewhat like classical joint probability distribution. So, you will get the marginal probability distributions, but this is not a proper probability distribution. Okay. Right. Yes.
Sorry to disturb. The camera has not moved towards the left window.
Oh, camera is not moved to this left window. What does it mean?
Means that the operator didn't move the camera towards you. We are seeing the right side board.
Oh, can you see this part?
So we are not seeing you.
This part.
This we are seeing.
But then what is the problem?
Left side,
I
left.
think he didn't move the cam. Means he didn't change to the.
What about this part? This part is visible?
No, sir.
Oh, how come?
Yeah, now only. Now we got more.
Okay.
Thank you, thank you.
I see. Okay. Thank you. Okay, good.
So is it correct to say that this encodes as much information about the state as the road? Whether it's specified
This
state
is
or
true for every phase space distribution function, not just Wigner function. So this is why we say that it is an alternative prescription of quantum system. Instead of your Hilbert space like density matrix operators, etc., you can do it in terms of the distribution function. Okay. Okay. Good. Right. So yeah.
here, how is the non-commutativity? So if I don't know about the operator, state operator, can I get that out of this?
Implicitly, yes. See, in quantum theory, we know that these two, of course, these are what these are called dimensionless quadrature operators, but that's okay. Still, they satisfy this thing, right?
So that's the question. So is this an input with the distribution functions? Or
Yes, yes, of course. I mean, you have to take this thing, right? A dagger is equal to 1, right? What is that? Yeah, this input you have to take. Yeah. So
this plus the distribution function is equivalent to the usual Hilbert space.
exactly, yes. In fact, that this becomes negative is an effect of this thing. Okay. Okay. Good. So now let me see. So the problem is there are too many things. I don't think I can go through all of them. This is too much for me. Okay.
Is there a book which collects all this?
Yeah, I gave these two papers. One is this, so two papers of Cahill and Glover.
Yeah, that.
So there you will get all this. Okay. But what I will tell in later classes, you will not find them. This is just a prescription for the formalism. Okay. So yes.
The region where the Wigner function goes negative
Yes.
is the signature of a purely quantum feature.
Exactly.
But when it is positive, it may be due to classical or quantum features. We may not be able to conclude.
Exactly. So I mean, this is a very good question you raised. So yeah, we'll talk about this with examples later. So yes. So the negativity of Wigner function definitely tells you that the state has some sort of non-classicality. That is for sure, because classical distribution cannot have negativity. On the other hand, if Wigner function is positive, does it mean that the state has no non-classicality? We cannot say that. So this we will talk about later, that the only phase space distribution function which can capture about classicality, non-classicality of states is through the P distribution. Nothing more, nothing less. Okay, good. Unambiguous, yes, unambiguous. In fact, this is historically also true, that people try to come up with some operational notion of non-classicality of states through some measurement statistics, photon number statistics, etc. Whatever people came up so far, all of them can be realized using properties of P distribution in principle. Okay. I mean, P distribution, as you know, that this is very, very badly behaved function, but this can capture everything. Okay. Right. So let me briefly mention about some of these properties of this T comma S, because that will be needed later, but I'll be very brief. What is the time now?
23.
Huh?
23, 323.
So, I will just briefly mention, and for you, you will have to check this thing, because I cannot prove all of them. This is too much for me, and these you can look at those papers for the derivation. Maybe not all the derivations are there, but anyway, at least some of you will have to dart your hands, and as people say that what is that saying, that
Devil is in the detail.
devil is there in the details. Yes. So better not to encounter the devil. Yeah, that you can do. Yes, but as a theoretical physicist, I don't know how will you escape that. Okay, good. So let us take this t of alpha 0. So this is for t of alpha s, and this is according to our definition, this is the Fourier transform of exponential of alpha beta star minus alpha star beta of d of beta s. Now s is 0, so then this is just d of beta. Okay. So yeah, so this you know. Now this you know that this is d of alpha t of, so basically the alpha dependence only comes in the displacement. So this is 0 0. So this is alpha is equal to 0, s is equal to 0, d of minus alpha. Is that a correct statement? And what is t of 0 0?
Lambda to power 0 to power.
Yeah, this integral. This is, yeah, this is you can look at there also. So this is basically beta belonging to c, because this will vanish. I mean, this will be 1. So this is d of beta, this square beta. So basically you take the sum of the displacement operators.
It is a ground state, right? Projector on the ground state.
Which one is ground state?
T00.
Why? What was your t? What was your t alpha 0 expression? T alpha s. What was that? This is 2 times d of alpha. No, what was the expression for this? Or even you can say s is equal to 0. So this is 2 times d of alpha minus 1 to the power a dagger a d of alpha minus alpha, right? This is the thing. So yeah, if you put this one, then t of 0 0, this will be 2 minus 1 to the power a dagger a. Yeah, that's it. And this is 2 times the parity operator. Yeah. So this is basically you'll have. Okay. Anyway, so so now I am not, as I said, I am not going to prove all the details. So what you can prove from here. So my point is that this t of alpha zeros, these are Hermitian operators, and they are orthogonal in the sense that you can show that trace of t of alpha 0 dagger, of course this is equal to t of alpha 0 because this is Hermitian, times t of beta 0, this is equal to, and this is where I am not going to prove anything, delta 2 alpha minus beta. So this is for you to prove. I hope you can prove it. So okay. So you have, I have given all the details. I mean, whatever is needed to prove this thing. So this is what you will have to prove. So what does it mean? It means that these operators are orthogonal to each other. Okay. Is that clear? Okay. Now let us suppose, this is again suppose or assume that. Assume that you have f is a bounded operator. assume that your f, as we have done it in terms of displacement operator, let us do it in terms of this T alpha 0. So, let us assume that this is 1 upon pi alpha belonging to C d square alpha. Here is the weight function which I will call alpha s is equal to 0 times P alpha 0. Remember what we did last time in terms of displacement operator, this is your weight function which is trace of f times displacement operator d alpha. Okay. Now, what we are doing is we are expressing f, which is a bounded operator, in terms of this is at the level of assumption, and one can prove that for bounded operator such an expression exists and this is convergent, everything can be done. Okay. Right. So, now if we take trace of f t of alpha 0, or if you have taken alpha, that is okay. So, you use this property and you can prove that this is nothing but f of alpha s is equal to 0. So, this corresponds to the symmetric ordering. So, basically this is what you will have. This is similar to what we have done for the displacement operator. Okay. Only thing is, now this is a Hermitian operator and we know what are its eigenvalues, eigenvectors, etc. Okay. Small f is the, see, my question point is, can I write a bounded operator as a linear combination of these operators? These operators we have shown that these are kind of orthogonal. So, in principle I can, this is a basis, so I can write it. Okay. Okay. And you can prove that norm of this f, which is non square, which is trace of f dagger f, this is same as norm of this f. Okay. This you can prove, there is nothing difficult about it. And one more thing that is also important, you remember we have described this outer product of two coherent states in this form, 1 upon pi gamma belonging to C d square gamma beta d of gamma alpha, then d of gamma. I think d of gamma or d of minus gamma, I do not remember, maybe this is a minus gamma perhaps. Okay. This we have done earlier, right. This is the kind of expression we have done. So, this means that these operators can also be written in the displacement operator basis. What you can prove is that this is also true. So, this operator can also be expressed in terms of this. Now, you may say that look, oh, why did you have to prove this thing, take this expression, and because this is bounded operator, this should hold good, that I have not proved. I have said assume this thing, but here you can actually prove this thing. Without that assumption you can also prove. Okay. And this proof, how will you go about that? As we have done in the case of displacement operator, take any two coherent states here. So, you take the matrix element of this operator with respect to these two coherent states and do it here also. What you should prove, that this left hand side is equal to right hand side for arbitrary eta and epsilon. Then of course, this will show that this operator is equal to this operator. Okay. Right. Okay. So, one more thing and then I will stop. So, basically the displacement operator and this operator T alpha comma 0, they will go parallel in parallel. In fact, this is true for alpha for other real values of S also, that we will see later. So, any operator, forget it whether it is bounded or not, I can write it in the coherent state basis. This you agree, right? Because I know that the identity is 1 upon pi alpha belonging to C d square alpha alpha alpha. So, on the left hand side and right hand side you put the identity, that operator, then this is what you will have. Now, you substitute for this the expression that I have written here in terms of T. So, basically what you will get is the following. You will get 1 upon pi gamma belonging to C d square gamma trace of f t gamma 0 times t gamma 0. Okay. Now, look at here, this is what you wanted to prove, right? You had this assumption, but now you have actual expression. Okay. So, this f, which is weight function, is basically this one. So, this is your f gamma s is equal to 0, okay, and this will be convergent whenever this is bounded operator. Okay. Right. Okay. And from here you can prove that trace of rho f is equal to 1 upon pi. So, from here you will prove that 1 upon pi alpha belonging to C d square alpha Wigner function of alpha star and then f of alpha 0. Okay. So, any operator f, you look at the corresponding weight function when you express it in terms of this T alpha 0, and you look at the Wigner function. So, then you see that this average value can be obtained through this integral. So, this we will talk about later. This corresponds to S ordering, symmetric ordering of this rho. This also corresponds to symmetric ordering of this f. So, in this average value you have the distribution function which comes from symmetric ordering, you have the weight function which comes from symmetric ordering. For any other distribution function, such thing does not happen. If you take p distribution here, which is normal ordering for density matrix, this one will correspond to anti-normal ordering. If you take q distribution, which is anti-normal ordering for rho, this will correspond to normal ordering. Okay. Only for symmetric ordering you will have such an expression where both of them corresponds to symmetric ordering. Okay. And yeah, so we will talk about it more details later, and then I will also consider other distribution functions and all that. So, for today let us stop here, and some of the things which I could not prove because of time, you can try to verify it. Okay. And as I said, this is something which you, unless you do on your own, you will not get confidence. Okay. Okay, thank you.